Okay, so in the previous lecture, what we did was we had two circuits, two different circuits, circuit 1, circuit 2, and we sent some current in circuit 1, let's say, and then we calculated its effect on circuit 2. Now, how was that effect? Well, you have a current carrying wire, it creates a magnetic field. It will create a magnetic field where you have your second circuit, and especially if you have a time-dependent current in your first circuit, it will create a time-dependent magnetic field, which will create an electric field at the point of your second circuit, and hence it will influence how the charges are, whether the charges are flowing, how the charges are flowing in the second circuit. So they will have some effect on each other. But you can also imagine just a single circuit. Let's say we have one circuit. We send some current through it. But if we have this current running through our circuit, our solenoid, let's say, as an example, there will be a flux built in this solenoid. There will be a flux in the solenoid, just one solenoid. We send the current, it will build a magnetic field, and hence there will be a magnetic flux running through it. This flux itself will also be proportional to the current running through the solenoid. And the proportionality constant is what we call the self-inductance. Now, in this case, we had already discussed this to some extent. We have this flux running in our solenoid. If the current is changing, this flux is changing in time. If we have a time-dependent flux, we know that it will be creating a back EMF. So there will be an epsilon, which will be given by minus d phi by dt, or this is minus L d phi di by dt. Now, if we connect it, so let's say that initially we don't have any current running through it, we have a battery. Well, once we turn on the battery, the current will try to build up. Now, up to now, we always said that, okay, when you close the circuit, that the current instantaneously starts. But you see, it won't be so. Because if the current starts instantaneously, it would just mean that the I by dt is huge. If the I by dt is huge, then the back EMF will be huge. So it just cannot be. It will resist the current. So the current itself, even if there is no capacitor or there is no resistor, etc., even if there is just one inductor, or even if you just take a loop by itself, it also creates a magnetic field. There will be a magnetic flux passing through this loop. It will take a finite amount of time for the current to start from zero to go up. Now we will discuss how long does it take in 10 minutes, let's say. But it will take some time. It will not be instantaneously building up. Now, before studying the circuits, let's look at this one. This is the back EMF. So if you want to increase the current by some amount, you still need to work against this back EMF. Now, if you remember the power of a given circuit element was epsilon times, what's the power? Epsilon times I. Okay. Now the total work that you have to do is the integral of the power over some finite time from, let's say, t initial to t final. This is the work that you have to do. If there's a power, this power will do this much work. Now in this example, we have the EMF. Let's forget the signs for the time being. We have the power, epsilon is L di by dt times I times dt. Well, you can just imagine to cancel these things. And what we have is L integral of I di. This is 1 over 2 L I squared, or delta I squared. So if you want to create a current running through a circuit element that has a self-inductance L, you have to be doing work against this back EMF. Now the back EMF is, we just said that it is L times di by dt. So that is it's minus L times di by dt. So the work that you have to do is L di by dt. If you just take this integral, you will get that this is the work that you have to do, is 1 over 2 L, the final current squared, minus 1 over 2 L, the initial current squared. So for the special case when the initial current is 0, the work that you have to do, the final current, let's say it's just I, is 1 over 2 L I squared. Now just compare this with the case in the capacitors. The idea is identical. In a capacitor, what we did was, as we are putting more charge on our system, there will be a potential which we have to work against it if you want to increase the charge in the capacitor. So we had to do some work, and the total work that we had to do is nothing but the energy stored in the capacitor, and this was the total energy stored in the capacitor. Now, just like that, in the case of an inductor, if you want to increase the current, start the current from 0 and increase it to some final value, you have to do something has to do some work against this inductor, because the inductor will try to prevent the current from changing. If it is initially 0, the inductor will just try to keep it at 0. So if you want to increase it, you have to work against the inductor. And the total amount of work that you have to do is given by 1 over 2 Li squared. This is the inductance, which just plays, in a sense, the role of 1 over C. Here you have the current, here you have the charge. So in a sense, the inductor itself is a storage of energy. Just like the capacitor stored energy in its charge, or we also said that the capacitor stores energy in the electric field inside the capacitor. An inductor stores energy in the current. It tries to keep the current constant. It will try to prevent the current from changing, let's say. And it will also be storing some energy in the current, or the current will be creating some magnetic field. We can also interpret this as an energy stored in the magnetic field. Now let's do that. Now first we need to calculate what is the self-inductance of a solenoid. Now what we have to do is, example, we have this solenoid. We wrap a wire around it. Now, what is the self-inductance? The steps are identical to the mutual inductance. We first set a current running through our system. This is let's say we have the current I. Now, this current will create a magnetic field inside the solenoid. Phi B is equal to mu0 N times I. This will be the magnetic field inside our solenoid. Now, since we have the magnetic field, we can calculate the flux. The flux inside the solenoid will be B pi r squared, let's say r is this radius, times the total number of turns in our solenoid. And since we know the B, this will be mu0 N I pi r squared large N, or this is equal to mu0 N squared over L pi r squared times I. This is the flux. The definition of the self-inductance is this should be L times I. So this constant over here is what we call the self-inductance of a solenoid of length L. Oops, sorry. L is mu0 n squared over d pi r squared. Now we can calculate what we are trying to do now. We know the self-inductance. We would like to write the energy stored in my solenoid as a function of the magnetic field inside the solenoid. That is what we are trying to do. Now the energy stored inside the solenoid is 1 over 2 L I squared. We had just calculated what L is. This is our L. And we can also write the current in terms of the magnetic field. This will be B over mu0 n. So we know the energy, we know the self-inductance, and we know the current in terms of the magnetic field. We just have to put them back. This is equal to 1 over 2 mu0 n squared, let's just d. Now n squared d is large N squared over d. Now this small n is nothing but large N over d. That's what I'm using. Times pi r squared. This is my L. I squared is b squared over mu0 squared times n squared. I just substituted everything back. I know what L is, that is this expression. I know what I is in terms of the magnetic field. So this is, I just put the square of this one over here. Now these ones cancel. What remains is omega is equal to 1 over 2 b squared over mu0 times pi r squared times d. Remember, I'm imagining a cylindrical solenoid, cross-sectional area pi r squared, and d is the height of my solenoid. So this is the cross-sectional area times the height. This is nothing but the volume of my solenoid. Now, if that is the volume of my solenoid, this I can just say energy stored in my solenoid per unit volume. But that is the energy density. Now let's just compare inductors and capacitors. Now the energy stored in an inductor was 1 over 2 Li squared. In a capacitor, we had 1 over 2C Q squared. In an inductor, the energy stored in the magnetic field density is 1 over 2 mu0 b squared. In a capacitor, 1 over 2 epsilon 0 e squared. They're quite similar. And an inductor will try to keep I constant if the I changes, there will be this induced back EMF which will try to eliminate this change, the effect that is causing this change in I. And in the capacitor, it will try to keep the Q constant. Well, in fact, it will try to keep Q is equal to 0. If there is a charge Q, it will just try to push it away. Does this remind you anything from mechanics? There's something which tries to keep one, and if you just compare these two, this is nothing but the rate of change of that one. I is the rate of change of Q. So here we have a system. One part of the system, now if you just combine these two, one part of the system will try to keep this variable at 0. And the other one will just try to keep the change of this variable constant. So it will try to keep the second derivative of this variable 0. Any mechanics analogs? Just to imagine a mass and a spring. If you have a spring, it will try to keep the mass at the equilibrium point. It will try to prevent its change. But the mass of this point mass, if it has a velocity, it will resist any change in the velocity. So we will see that this system, if you just combine a capacitor and an inductor, it is actually identical to our oscillator system. Now we will see the circuits in a moment, but any questions on this one? So again, just like in the case of the capacitor, if you remember, when we were studying the capacitors, we first calculated how much work we should do in order to charge the capacitor. Well, we did the same thing here. We just calculated how much work we have to do in order to create a current running through our inductor. Because the inductor resists changes in the current, we have to start the current from 0 and reach some final value. In this time, we have to do some work, and that work is stored in the inductor. That was the first step. Now, in the capacitor example, as a second step, we just said that, okay, the energy stored in this capacitor, we could interpret it as energy stored in the electric fields inside the capacitor, not on the charges, but the electric fields. In the case of the inductors, we did the same thing. As we are building the charge, building the current in the inductor, there's a magnetic field. We are creating a magnetic field in the inductor, and the energy stored in the inductor, we could interpret it as total energy stored in the magnetic fields inside the inductor. And the energy density in the magnetic field is proportional to the square of the magnetic field, just like the energy density in the capacitor in an electric field was proportional to the electric field squared. So this electric field itself stores energy. Magnetic field itself stores energy. So they have their own energy. So this is our one step towards proving that the electric and magnetic fields, although initially we just invented them, just out of nowhere, let's say, we invented them, we invented these mathematical objects, but now we see that these mathematical objects have their own energy, they carry energy. So we will also see that they can even have momentum, and hence they have their own physical existence. Any questions? Okay, how? So there's magnetic, we said that magnetic field doesn't do any work because the force due to the magnetic field is always perpendicular to the displacement. So it cannot do any work. So how come we are doing work? We are? Well, you see, what we did was we calculated the work that we had to do in order to build up this current in the insulator. We are not doing work against the magnetic field, but still the work that we have done is kind of converted into energy stored in the magnetic field. That work, well, if you are doing work, you are transferring energy to your system, and that energy has to be stored somewhere. the changing magnetic field. Now what we are actually doing work is we are changing the magnetic field by increasing the current. Now this changing magnetic field creates an electric field. And we are doing work against that electric field. And hence we have to do that work against the electric field. Now where does that work go to? There is no energy dissipation. There is no electric field buildup. Well, that work that we have done is basically used to change the magnetic field. We are not doing work against the magnetic field, we are doing the work against the electric field created by this changing magnetic field. And the energy that we transfer to the system is used up to change this magnetic field. And hence it is stored in this magnetic field. Kind of. I mean, it's just like this example when we had this rod moving in a uniform magnetic field. We had to do work if we want to keep the rod moving at constant velocity. But again, we are not doing, the magnetic field is still not doing work. The magnetic field just behaves as a, let's say, a converter of mechanical energy into electrical energy. Any other questions here? Well, let's first start with LR circuits. We have a solenoid. Well, this is the symbol that we will be using to denote solenoids. An inductor. And let's say we have a resistor. And somehow we just build up some current in our system by some means. Let's say this is the positive direction of our current. Now then the question is, how can we determine how does this current change as a function of time? Well, let's just use the Kirchhoff's rules. Now the Kirchhoff's rules we interpreted in the form that as you go around the circuit, there should be, the potential difference should be 0, but we can also reinterpret it as we go around the, if we take a test charge and as we go around the circuit, the total work done on this test charge should be 0. Because when we go back to our initial point, it has the same energy, same potential energy, same kinetic energy. So the net work done on a given positive charge as we keep moving around the circuit should be 0. Whether the forces are conservative or not, we don't really care. We have to calculate the work done on a given unit charge as it is actually moving around the path. Now let's start from point A, B, C, and D. This is the positive direction of our current. Let's say that there is this current running at this instant. Let's just follow one positive charge. One positive charge as it moves in the direction of the current, what will be the work done on this? Will it lose energy or gain energy as it goes around the resistor? It will lose energy. Minus, all right. Well, you can just say that since we are assuming one unit charge minus R dq, well, eventually we will consider one unit charge per unit time. It will be dq by dt, which we define as I. Now, as we go around the inductor, will it lose or gain energy? Well, let's see. It will be L di by dt. Now, this is definitely true. The problem is, will it be positive or negative as the current is running? Now, let's take a particular case that let's just assume that at a given instant the current is decreasing. Now, if the current is decreasing, then di by dt is negative. But if the current is decreasing, the inductor will try to keep the current at its value, so it will be try to push the current in its current direction. So it will be doing some work on my system, on my test, on my charge as it's going through my inductor. It is trying to increase the current. So that's why if di by dt is negative, my inductor will try to increase my current. So it will be just pushing my point charge in this direction. So I will have this minus sign. It should be positive. This is negative. If this is negative, this contribution should be positive. So I should put a minus sign over there. I started here as I went following this current. As I went across the resistor, I lost this much energy. As I went across the inductor, I gained this much energy. The net change in my energy of a unit charge per unit time should be 0. Any questions on this one about the signs? So you see, so what does an inductor do? This back EMF in the inductor. It will try to, according to the Lenz's law, it will try to prevent the change in this current. Okay? So if the current is getting smaller, it will try to increase the current. It will be pushing the current in its direction. So if I'm following the current, if I take a unit charge dq, I'm following the current. The unit charge, the unit positive charge will lose some energy across the resistor by Ri. But the inductor is pushing my current in its own direction. So my unit charge is moving in this direction. So the inductor is pushing my unit charge in the same direction, so it's doing some actual positive work. I lost this much energy. Across the inductor, I should gain some energy. There's some work done on the mass, a positive work. Now, this is true if di by dt is negative. So if di by dt is negative, this whole thing has to be positive. So I should put a minus sign over there. Of course, this minus sign is valid whether di by dt is positive or negative. It is always the minus sign. But we just looked at a particular case when di by dt was negative, and we determined that this sign should be negative in that particular case, but this sign just doesn't change for the other case. I mean, we could just say, let's just look at the other case. Suppose at a given instant, for some reason, di by dt is increasing. My current is increasing in my circuit. Then what will it do is if I go in the direction of the current, this inductor will try to prevent me. Because since the I by dt is increasing, the inductor will try to lower the current, reduce the current. In order to reduce the current, it has to work against any charges trying to cross the inductor. So if the I by dt is positive, as my positive charges move from B to C in the direction of the current, the inductor should be working against them. So I should add this term should be negative in that case. And you see, if the I by dt is positive, this whole term should be negative, so I should have this minus sign. It's the same sign whether the I by dt is positive or negative. The points between B and C is the same as the potential difference between A and D, and I would say that it is just Ri. when you have inductors and inductors, it doesn't really make too much sense about talking about potential differences. You see, when you have a changing magnetic field, the electric field, electric force is not a conservative force, so you cannot really define a potential. So whenever you have inductors, you should stop thinking in terms of potential differences. Whenever there are inductors or changing magnetic fields, just forget about potential differences. It doesn't make too much sense because the electric field is not a conservative force field anymore. Okay, sure. If there is no changing magnetic field, then the electric field is a conservative force, is a conservative field. Since it's a conservative field, we can define an electric potential corresponding to electric field if magnetic field is not changing, or if there is a constant current. Not necessarily, I mean, even if the current is changing, a direct current is usually a current that is flowing in the same direction all the time. Its magnitude might still be changing. Even if the magnitude is changing of a direct current, you still cannot really define a potential difference. At one instant, is there a changing magnetic field? Okay, still, you can define the derivative at that time. As long as the time derivative at that time is non-zero, you cannot define potential differences. Now, you are doing work in the inductor. The inductor will be doing work against you. You are just not doing work against the magnetic field. You are doing work against the inductor. Sure. I mean, in the inductor, if you have a changing magnetic field, there will be an electric field, and hence you are working against the electric field. Don't think in terms of the potential. So you just want to go from A to D to C and to B. From here to here. Okay. Now, first let's finish this one. And then we will discuss what happens if you go the other way around. Well, I will still call it the potential difference. I will treat it as a potential difference. But the potential difference between A and D, I will still do that. But just keep in mind that the definition of a potential difference in a region where there is a changing magnetic field. Well, I will still call it a potential difference because here, ideally, there is no magnetic field. In this region, there is no changing magnetic field. So I can talk about the potential difference between A and D. I can still do that. But if I want to talk about the potential difference between B and C as I go across this wire, that is what I cannot do. Because as I go from B to C, there's a time-dependent magnetic field. I can talk about it over here. Well, if you are happy to identify the potential difference between B and C as the potential difference between A and D, that's still fine. But the potential difference between A and D will not be equal to the integral of the electric field as you go from B and C across this wire. That is what is different now. That is the EMF created by this inductor over there. In a sense, you can just think of this as a battery in itself, and that battery creates such an EMF. Other questions? Well, that is what the inductor does, or the magnetic field does, let's say. The magnetic field will, if you change the magnetic field, it will try to prevent that change by creating some additional currents in your system, trying to create additional currents in your system so that the magnetic field will be constant. But that just translates into keeping the current constant. For what? It will always resist. Whatever the number of the turns is, whatever the radius is, etc., it will always resist. Will it be successful in resisting it? Well, let's solve this and let's find it. And will it be possible to create an inductor such that it will keep the current constant in this system? Okay, using energy conservation, it shouldn't be. Because if the current is running, you are dissipating energy. If you are dissipating energy, where does that energy come from? It is nothing but the energy stored in your inductor. There's a magnetic field inside your, as long as there's a current, there's a magnetic field inside in your inductor which will keep the energy constant. Well, it will be giving you the energy that you dissipate through the resistor. Now, if you want the current to run for a long time, you have to make sure that you store a huge amount of energy in your inductor. The larger the energy you store in your inductor, the longer the current will run. If you want to store a large energy in your inductor, you should have the self-inductance, the inductance of your inductor to be huge. L should be large. The larger it is, the longer the current will last. But there is no value of L for which the current will last until infinity. It is against energy conservation. Well, rechargeable batteries are not inductors, but the charging mechanism uses inductors. For example, if you have these electric toothbrushes, you just put it on some place. There's no wires over there. They are just charged. What is happening over there is this one. You have one coil in your charger, another coil in your toothbrush. And you don't need to connect it. There is no need for current to flow directly from one to the other one, as long as there is a changing magnetic field. But the city electricity is already a changing current. So you provide a changing current, which creates a changing magnetic field, which induces a changing flux over here, which creates this current. Yes, more or less. So you are actually using these systems. Or now some of the phones, the smartphones, they have these wireless chargers. It's exactly the same mechanism. The thing that charges your phones contains some coils in it. And your cell phone contains some coils also. And by induction, you create currents in your cell phone which charges your cell phone. Now let's go back to this example. Now, what do we expect? We expect the current to last a longer time if L is large. That is one expectation, because just using energy conservation. If R is large, the current will not last long, because if you keep L constant, that means the initial energy that you have in your system has some value. If you increase R, it just means the dissipation will be larger. If the dissipation is larger, so it won't last long. So how long it lasts should depend on L over R somehow. Now if you look at this relation, we have, this is our equation. L di by dt plus Ri, this is equal to 0, or di by dt is equal to minus R over L times I. So we have this I should be such a function that its derivative should be equal to itself. Do you know any such functions? The logarithm, the derivative of the logarithm is 1 over the argument of the logarithm, so it's not the ln. The exponential, the derivative of the exponential is itself. So this is how the current will be changing in time. Now, as we expect, if R is large, then this exponential will just decay off very fast. If L is large, then it will decay slowly. So it will have this dependence. This is T, this is I, so this is I0. Let's say this is I0 over 2, this is T1 half. What is T1 half? Yes. What's it, I mean, from this expression. Okay, I0 over 2, this is equal to I0 e to power minus R over L T1 half. If you take the logarithm of both sides now, this was an exercise in your experiments, this is minus the logarithm of 2, this is equal to minus R over L T1 half, or T1 half is equal to L over R logarithm of 2. Now here we also have something called the time constant, but this time the time constant is just L over R. In the capacitors, if you remember, it was just RC, or 1 over RC. Now here it's L over R. And as we expected, if L is large, the half-life gets very large. If R is large, the half-life gets very small. But there is no value of L or R for which the half-life goes to infinity. It always takes a finite amount of time to be halved. By the way, is the units correct? I mean, checking the units is just the shortest thing that you can do if you want to test whether your answer seems to be correct or not. Now, what is the unit of L? Now, let's see how we can determine L. Just if you know any equation in which L appears, now from this equation you can just determine the unit of L. L is equal to the unit of epsilon times the unit of time divided by the unit of the current. What is the unit of epsilon? Is it volt or joule? What's the difference between volt and joule? Joule is energy, volt is energy per charge. What's the unit of time? I is ampere. This is what we call the Henry. Okay, this is the unit of L. Now let's see, what's the unit of L over R? Now if this is true, half-life has units of time. It should be seconds. Is it equal to seconds? Now let's show it. It should be equal to seconds if we did everything we did is correct. Now L over R, we already calculated the unit of L, which is volts seconds per ampere. What is the unit of R? Resistance. It is ohms, which is volts per ampere. Volt cancels, amperes cancel, so its unit is seconds. So things seems to be correct. Now it did satisfy our expectations that the larger the L, the larger the half-life should be, the larger the R, smaller the half-life should be. So we had that expectation even before solving the problem. Now it's actually, we see that this result satisfies our expectations and the units are also correct. So most probably we have a correct answer. The only thing we might be missing is just maybe some factors, some numbers. Any questions before the break? Okay, see you after the break.